Continuing our discussion of forces is the second video on free body diagrams. A free body diagram is a way that we can visually represent all of the forces that are acting on an object so that we can analyze these forces. What really matters is not a single force acting on an object, unless that's the only one, but it's the total of all the forces. And when the problems get more complicated, it's very helpful to have a diagram that shows us all the forces and the directions that they're acting. The forces will be shown with vectors, or the forces are vectors, and we'll use arrows to represent them. The length of the arrow will represent the magnitude of the force, how big it is, and we'll draw it in the direction that the force is acting. In an FBD, we isolate the object. You don't draw a free body diagram of a system of things. You only draw a free body diagram of a single object. So we isolate that object from its surroundings. Identify contact forces first. They're the easiest ones to think about. Is there anything touching your object that is exerting a force? Draw those in, thinking of the magnitude and direction. Are there any field forces acting? Gravity almost always acts. So you'll almost always be putting an mg, or a gravitational force vector, on your force free body diagram. And is there a normal force? In what direction will it act? Now, the normal force, remember, is a support force. We'll get into some detail about it in when we start talking about Newton's third law. But it's a support force, and it always acts perpendicularly to the surface. If an object isn't resting on a surface, there won't be a normal force. To draw the free body diagram, you start by representing the object with a box or a circle. So you can draw a box that represents your object, or you can draw a circle that represents your objects. And as we said before, every force that's acting, we represent with an arrow. The length corresponding to the magnitude, and the direction corresponding to the direction of the force. All arrows point away from the object. So free body diagrams, look like this, or like this. The arrows start on the object and go away. They never, ever, ever look like that. That is not how you draw a free body diagram. So arrows should always be pointed away from the object. It's the direction that force would move that object in, the direction that the force is pushing or pulling. Even if a person is pushing on a box behind, this person is pushing that box, we would draw the force that person is exerting like that. It's the direction that the force that they're applying would move that object. Okay? So let's start easy. You have a book that rests on a tabletop. Diagram the forces acting on the book. So we have a tabletop, and there's a book that's sitting on the tabletop. It's not a very good table. Go with me. Okay, so look at the forces that are acting on that book. So we'll draw the box that represents the book. Well, gravity is acting, and I label gravitational forces mg. You can label them fg if you want to, but I like mg. And that's not the only force acting. Well, how do I know that? Well, we haven't talked a whole lot about balanced forces, and that's kind of Newton's first law, which is the next video. But if that's the only force acting, this thing is falling. If it's sitting still, there's got to be something that's keeping it from falling with the gravitational force, and that's the support that the table's giving. That's our normal force. So we draw the normal force upward. Now, I wasn't really careful about length. I didn't pull out my ruler tool and make them exactly the same length, but they do look like they are about the same length. If you know they're not supposed to be, if you know one force is bigger than the other, exaggerate it a little bit so that it's obvious. A ball is suspended motionless from the ceiling by a rope. Here's our ceiling, here's our rope, and our ball is suspended. Diagram the forces that are acting on the ball. Well, I'll use a circle since it's a ball, and gravity's acting. Gravity will almost always be acting. I usually draw it first because it's almost always there. Now, there's no normal force in this case. If that ball had been sitting on a tabletop, there'd be a normal force. But there's no support force pushing up on the ball, perpendicular to the surface, so there's not a normal force. But what there is tension pulling up on the ball, which is another kind of support force. And that ball's not accelerating. It's not moving. It's motionless. So I'm going to make the two arrows the same length. And I label tension forces with a capital T. If you would like, you can label it with a capital F and a subscripted capital T. An egg is free falling. Now, what did free fall mean from the last chapter? Free falling means there's no air resistance. Free fall is an object falling under the influence of only the gravitational force and nothing else. Well, that makes this a really easy diagram to do. Here's our egg, and if it's only under the influence of gravity, well, there's our gravitational force, and there is nothing else. If there were air resistance, I would draw an upward arrow representing the air resistance, but there isn't any. A flying squirrel is gliding from a tree to the ground at a constant velocity. Consider air resistance. Diagram the forces acting on the squirrel. Well, here's our squirrel, and there's our gravitational force. Now we have to draw air resistance, so I'm going to have an upward arrow, and I have to think about how long does it need to be? Does it need to be the same length as my weight? Longer, shorter? Well, the question is answered right here. It's falling with a constant velocity, and that means that the forces on it are balanced. It's not accelerating. And so I'm going to draw the air resistance vector just as long as my weight vector. I label air resistance AR. You can label it F, AR if you want to, but I just used AR. Okay, so there's no acceleration. The forces are acting equally. The sum of the forces would be 0. A rightward force is applied to a book in order to move it across a desk with a rightward acceleration. Consider frictional forces. Neglect air resistance. Diagram the forces acting on a book. So we have our tabletop and we have a book, and somebody is pushing that book to the right, and it's accelerating, and there is friction. Okay, so here's our book. We know there's a rightward force, and I'm going to call it FA for F applied. There's gravity. Oops, that should be straight down. And there's the normal force, which will be straight up. And there's friction, so I have to think about, notice I made my normal force and my weight vectors equal sizes. The thing's not flying up into the air or falling down, so the forces are balanced there. But in this direction, they're not balanced. There's a rightward acceleration. And that means the applied force has to be bigger than the frictional force. And so I'll draw a frictional force arrow, but it'll be sort of small relative to the applied force. Force is on an incline. Okay, let me draw an incline. If I have an object that's sitting on an incline, I would draw it like this. Okay? Think about the forces that are acting. Well, there's weight, certainly, and the weight acts down. The normal force, now the normal force is always on every free body diagram that we've done so far. If there was weight and a normal force, it looked like this. The normal force straight up and the weight straight down. Normal is a math word that means perpendicular. The normal force acts normal to the surface, and so the normal force will actually be in a direction like this, perpendicular to the surface. So we have weight, we have the normal force, and it's the ramp is a rough ramp, so we have to include friction. Well, if it's sliding down the incline, if the motion is in this direction, then friction will oppose that motion, and so the friction arrow will be in that direction. And I like to label friction with a lowercase f. If you want to label it like that, you certainly can. This box is suspended by 2 ropes. Draw the free body diagram. Here's our object. There's certainly a gravitational force. There's no normal force because the box isn't resting on a surface. There are two tension forces that are holding the box. And the tension forces go off at angles. And so I'll draw one tension, and I'm going to label it T1. And then I'll draw the other tension, and it's off at a different angle. So, well, let me undo that. I didn't quite get it off at a different angle, did I? And that'll be T2. And those are the only forces acting on the box. Okay, I think that's it. Nope, one more. Oh, that book in the previous example, the one that had the rightward acceleration, suppose that you stopped pushing it. So the book is sitting on the tabletop, and you're pushing it to the right, making it accelerate. Well, what if you took your hand off the book? Well, it's not going to immediately stop, but it'll stop pretty quickly because of the frictional force. It'll slide to a stop. So let's draw the free body diagram after you stop pushing it while the book is still moving across the table. So here's our box, our book. Weight and the normal force, equal and opposite. Okay, it is still moving to the right. It hasn't stopped moving yet. You pushed it, you accelerated it, you stopped pushing it, it's going to slide to a stop. But there's no rightward force anymore because you're not pushing it. But there is still a frictional force. Now this reminds us that free body diagrams don't tell us how the object is moving. They tell us how the object is accelerating. There are unbalanced forces horizontally here. The only force acting is to the left, so the acceleration is also to the left. Since the velocity is to the right, if the acceleration is to the left, that means it's slowing down. Okay? So keep in mind, we're not diagramming the motion, we're diagramming a change in the motion. Free body diagrams tell us about acceleration. They don't tell us about velocity. I want you to think about the example a free body diagram that looks like this. Weight down, and I'm going to put an arrow up and I'm not going to label it. I'm just going to say there's an upward force. You cannot look at that and tell whether the object is moving or whether the object is stationary. All you know is that it's not accelerating in this direction because those two forces are equal. And so if this were a case of an object that has reached terminal velocity, and we'll talk about terminal velocity in detail later, but if it has, then it's falling, but the air resistance and the weight are equal, and so it's not accelerating. This could be that ball that was suspended from the ceiling. The free body diagram looked like this, only the upward force was tension, and that wasn't moving. So this is the diagram for an object that has vertical forces on it, but is in equilibrium. Might be moving, might not be moving, but it's not accelerating. So free body diagrams tell us about acceleration. They don't tell us anything about velocity.